Hi all and welcome. My name is Chris Goodwin, a member of DSC 680 at Bellevue University. Today, as you can see from this title slide, we are going to be talking about the power of the quarterback, predicting NFL outcomes using only QB statistics. We'll be taking a look at historical quarterback data and seeing if we can use it to predict the outcome of professional football games. Now, I couldn't do this presentation without giving a shout out to Buffalo Bills quarterback Josh Allen, who you see pictured here. His excellent play this season has given the Bills their best record of my lifetime and an AFC East division championship. They play the Colts on Saturday, and I just wanted to say good luck, Josh. Let's now move on to a brief introduction of this topic. For fans of American football, it is well known that the quarterback, or QB for short, is the most important position in the game. A football QB, like no other role at any team game, normally reflects his execution on the final score. It's atypical that a bad day for a QB could translate in a good day for the rest of the team. Excluding a few anomalies, the quarterback is the key for wins and championships. In 2019, the Harvard Business Review posted an article declaring the QB the most important position in all of football, and that included the coach, general manager, and even the owner. These four positions explained roughly 68%, or more than two-thirds, of the variance in team performance. Owners carried the least weight of these four with roughly 11% of explained variance, and the quarterbacks led the way with roughly 37%. The goal of our presentation is to take that even a step further. Within the QB position, what variables factor most heavily into a win? By looking at game logs throughout the course of league history, we can determine which statistics, such as sacks, interceptions, passing yards, and touchdowns, lead to the most victories. We need to start by examining the data we will be using in our analysis. So I found a data set called NFL Statistics from Kaggle user Kendall Gillies. This data was scraped from NFL.com using a Python code. Within this data set, there was a grouping of QB game logs. Each row of the quarterback game log database represents an individual game for an individual quarterback. We had to make a few minor updates to the data set before we could do our analysis. The first step was removing all entries where season equals preseason. The preseason is played much differently than regular season, where an individual player may only play a few plays. Including this data could sway our results, so I chose to remove it. The second step was removing any entries where passes attempted equal --. When evaluating QBs, we obviously want to only include players who threw a pass. Whether the data was missing from the scrape or if the player truly threw no passes, we want to exclude those game logs. The final purge comes from those game logs where outcome equals T. This indicates that there was a tie. There are two main reasons for us to eliminate these entries. One, we really are only trying to predict wins and losses. And two, ties are so rare in the NFL that it would be unfair to our model if it had to predict them. Fourth step was for any null values, the string ---- was uploaded to indicate a lack of data. We already removed the data when the null variable was passes attempted. But for the rest of the data set, I made the decision to convert these to zeros. There were too many values to exclude completely from our analysis. For example, if we dropped all NA values, there just would not be enough data left. So I felt like making them 0 was a good way to go for our analysis. In addition to that, in order to clean some of the data points up, I converted any numeric data to the appropriate format. Some of the integer and float variables were being portrayed as strings or objects, so I made the necessary adjustments. And in addition, some of the variables of interest needed to be converted to categorical in order to perform our analysis. The final step was creating some additional variables of our own. The first new variable was called team points. This column represented the amount of points an individual's team scored during the game. This value was parsed from the score variable, which included the combined score for the game. The other variables were encoded categories. I encoded home or away, where home was represented by a 1 and away by a 0. I also encoded the opponents, which were numbered 0 to 31 to represent the number of teams in the NFL. And then the final encoding was for the outcome of the game, with a win being represented by 2 and a loss by 0. What we are left with is roughly 17,000 game logs with approximately 35 variables. Our first step was to really take a look at the data and see if we could gain anything just from its general distributions. In order to do this, I compiled some distribution plots for a few variables of interest: passing yards, touchdown passes, and team points. I chose these 3 variables because based on my general knowledge of football, I thought they may be particularly important. In row 1 of the graph we see here, we can see that there's distributions for the 3 variables for all QBs in the data set. After our initial data cleaning that was described before, these distributions represent the entire set. We then have a second row labeled winning quarterbacks. These distributions only represent the quarterbacks who won the game. We see that for all 3 of these variables, there is a general shift to the right when we only include winning quarterbacks. This means that there are fewer lower values and more higher values, i.e. quarterbacks who throw for more yards, complete more touchdown passes, and score more points tend to win more often. Another good way to look at our data is to create a pairwise plot. This creates scatter plots of every variable in our data set. This could give us some real insight into our data and how we need to go about building our model. In order to create this plot, we only looked at the numeric data that is included, which did include our encoded categorical variables that we created previously. We see this plot on our screen here. And while the pairwise function is a pretty awesome tool, unfortunately for our analysis, it does not tell us much. First off, due to the number of variables we have in our data set, it is difficult to fully read each individual plot. From this exterior view, the vast majority of scatter plots appear to be random, but it's hard to say for sure. I would not say any of these variables appear to be very strongly correlated, and it is even harder to tell the correlation with our decision variable outcome because it is categorical. Perhaps a more interesting look into our data would be a correlation matrix. As we can see from this chart, this is much easier to read. Most of the variables do not seem to have a strong individual impact on the outcome of the game. Team points seems to be the only variable with a noticeable correlation, which makes sense because more points typically lead to more wins. There are also a few variables that have strong correlations with one another: passes completed and passes attempted, sacks and sack yards, passes completed and passing yards. The decision we have to make is whether or not to include all of these variables with high correlations. For completeness of analysis, I have decided to include them. I think despite their high correlation, each individual statistic plays a role in the ultimate model. Now that we have cleaned up our data and have done our interim analysis, it's time to get to the nitty-gritty of the presentation, which was the building of our models. I ultimately used 7 different models, and we will get into each of them more specifically as we go here, but I wanted to do a brief introduction on how these models were built. All of the models we created using the scikit-learn package in Python. For those who are unaware, scikit-learn is a free software machine learning library for the Python programming language. It features various classification, regression, and clustering algorithms, and is designed to interoperate with the Python numerical and scientific libraries NumPy and SciPy. It truly was the perfect choice for this project. From there, we had to determine what our x and y variables were. Our x variables are composed of all of the numeric values in the dataset minus the outcome code, and that is because outcome code is our y decision variable. That is what we are trying to predict, the outcome of the game. We then had to split our data into training and test data sets. I chose to use an 80-20 split, which means that 80%, or almost 14,000 of the records, were used to train the model, and then 20%, roughly 3,000 records of our set, were used to test the model. The first option I chose was the decision tree classifier. A decision tree is a simple representation for classifying examples. It is a supervised machine learning where the data is continuously split according to a certain parameter. Because the variable we would like to determine is categorical, win or loss, we use a classification tree. Such a tree is built through a process known as binary recursive partitioning. This is an iterative process of splitting the data into partitions and then splitting it up further on each of the branches. As we can see here, when predicting the outcome, our model had an accuracy score of roughly 0.75, meaning that roughly 75% of the time we can predict the winner of a football game just using the quarterback's game log. That's a pretty impressive start. Within the model, we can look at the importance factors for each of the variables. The table on the right lists each variable and its corresponding importance. What insight can we gain from this table? Right off the bat, we notice how important the team points variable is that we created. Almost 40% of the importance is attributed to this one variable. On the other end of the spectrum, we see that some variables are not very important at all. Surprisingly to me, the home or away variable did not have much of an impact on the model. I would think that being a home team would have a large impact on the number of wins, but that is simply not the case. Same goes for touchdown passes. I would have assumed that touchdown passes would have had a great impact on the outcome of a game, but from our analysis here, we see that's really not the case. Because team points carried such a large burden of the model, I wanted to create another one excluding this variable. I followed the same process, but dropped team points from our X variables. This new model still achieved an accuracy score of roughly 0.68, meaning that it was able to successfully predict the winner of 68% of the games. In this new model, the variable passer rating actually became the most important, with an importance factor of 0.23. Another classification model that I wanted to take a look at was the logistic regression model. Logistic regression is a machine learning algorithm for classification. In this algorithm, the probabilities describing the possible outcomes of a single trial are modeled using a logistic function. Logistic regression is designed for classification and is most useful for understanding the influence of several independent variables on a single outcome variable. This is like a perfect description of what we are trying to do, so I felt like it was a perfect choice for us. As we can see on the screen, this model achieved an accuracy score of roughly 0.81, meaning that this model correctly predicted the outcome of almost 81% of the games. Let's take a look at the confusion matrix for some insight. We can see here that there were 2,780 correct predictions and only 656 incorrect. This leads to a precision value of 0.81, a recall value of 0.81, and an F1 score value of 0.81 on the entire data set. These are excellent numbers for our analysis. The third model that I wanted to take an in-depth look at is the random forest classifier. This is somewhat of a piggyback off of the decision tree algorithm. Random forest classifier is a meta estimator that fits a number of decision trees on various subsamples of data sets and uses average to improve the predictive accuracy of the model and controls overfitting. As we can see from the screen, the accuracy score for this model was roughly 0.8, meaning that the model correctly predicted 80% of the games, 80% of the outcomes for the games in our test data set. If we once again look at the importance of each variable, not surprisingly, team points once again dominated. The graph really puts into perspective just how dominant the team points variable is. It also goes to show that passer rating is also very important. This was somewhat predictable given the fact that the decision tree classifier we created, excluding the team points variable, had passer rating as the most important. But still, passer rating is almost doubly more important than any other variable in the data set. The importance of this passer rating stat leads me to believe that this is why ESPN dedicated time and resources to creating the QBR statistic. ESPN's total quarterback rating, or total QBR, which was released in 2011, incorporates all of a quarterback's contributions to winning, including how he impacts the game on passes, rushes, turnovers, and penalties. Also, since QBR is built from the play level, it accounts for a team's level of success or failure on every play to provide the proper context, and then allocates credit to the quarterback and his teammate to produce a clear measure of quarterback efficiency. Because QBR was specifically designed to judge for success, I feel like it would have been a welcomed addition to this data set. My gut tells me QBR could have been a really heavy player in these classification models. Finally, we will take a brief look at 4 more models. These did not have the accuracy to rival the random forest or logistic regression models, so I did not go too in-depth on them. But as we can see here, we have naive Bayes. This algorithm is based on Bayes' theorem with the assumption of independence between every pair of features. Naive Bayes classifiers work well in many real-world situations, such as document classification and spam filtering. This algorithm requires a small amount of training data to estimate the necessary parameters. Naive Bayes classifiers are extremely fast compared to more sophisticated methods. On our test data, this model achieved an accuracy score of roughly 0.75, meaning it correctly predicted the outcome of 75% of the games. We then move on to k-nearest neighbors. Neighbors-based classification is a type of lazy learning, as it does not attempt to construct a general internal model, but simply stores instances of the training data. Classification is computed from a simple majority vote of the k-nearest neighbors of each point. This algorithm is simple to implement, robust to noisy training data, and effective if the training data is large. On our test data, this model achieved an accuracy score of roughly 0.76, predicting almost 76% of the outcomes. This number seems to be right around the sweet spot for a lot of these models, the 75 to 76% range. We then have a stochastic gradient descent. Stochastic gradient descent is a simple and very efficient approach to fit linear models. It is particularly useful when the number of samples is very large. It supports different loss functions and penalties for classification. On our test data, this model only achieved an accuracy score of 0.67, meaning that it correctly predicted roughly 2/3 of the outcomes of the games in our data set. Finally, we have the support vector machine. Support vector machine is a representation of the training data as points in space, separated into categories by a clear gap that is as wide as possible. New examples are then mapped into that same space and predicted to belong to a category based on which side of the gap they fall. This algorithm is effective in high-dimensional spaces and uses a subset of training points in the decision function, so it is also memory efficient. Unfortunately for us, this model was only able to obtain an accuracy score of roughly 0.54, meaning that it barely was better than just the flip of a coin. So where do we go from here with this model? I think there are definitely some things we can do to improve. Step 1 would be to find or create a more complete data set. In our initial steps when we were cleaning the data, I eliminated entries where passes attempt equaled that -- null value, and by doing so we lost almost half of our data set. I can't help but think this hurt the models in the long run. If we had more instances to train the model on, I believe it would improve on its score. In this very basic example, we were able to achieve accuracies of over 80%, and I think the sky is the limit if we have more data. This also includes the possible additions of some new variables. As I mentioned before, we have the total QBR statistic, which I think could be very helpful. And there are more advanced quarterback statistics now that I would like to look into and wish I could include in these models because I think it would really help. Another step to take would be to include contributions from other players besides the quarterback. On any given play, there are 22 players on the field, and we only are looking at one of them. If we were able to incorporate different positions on the field, I think we could improve the models drastically. Another question to ask ourselves is, what can we do with these models? What positive outcome can we gain from doing this research? For coaches, I think it may sound overly simple, but your ultimate goal should be to score more points. Legendary football coach Paul Bear Bryant famously said, "Offense sells tickets, defense wins championships." That appears to be an outdated sentiment now, as we showed here that the main key to success is scoring points. What about passer rating? What can we do with this information? The NFL passer rating formula ranges on a scale from 0 to 158 based on completion percentage, yards per attempt, touchdowns per attempt, and interceptions per attempt. So it essentially encompasses a lot of other stats in our database. A higher passer rating typically means you are the better quarterback. This further solidifies the position that quarterback is the most important position on the field, and teams need to dedicate their time and energy to finding the right one for their team. Recruiting, scouting, drafting a QB needs to be a team's top priority until they find one. If we look at the Buffalo Bills, they missed the playoffs for 17 straight seasons before they drafted Josh Allen, and now have made it 3 out of the last 4 years because they found the right quarterback. This research might also help the ever-growing world of sports betting. January through August, revenue totaled about $178 million in the sports betting realm. Hundreds of millions of dollars are spent every year, so we might as well spend those dollars wisely. If we take into account how much a team scores or what the QB's passer rating trends are for the season, can we make an educated guess on what the outcome of a game will be? My thinking is yes, absolutely. If nothing else was gained from this presentation, I hope I could help you win a few bucks. Thanks for taking the time to listen. I really appreciate it, and let me know if you have any questions.